All right, students, I'm going to try another one here, one that can be a bit tricky. This is the ramp and the pulley one with some static friction. I think a two-object one as well as the static friction can be a bit challenging. So I see why a number of people are asking about this one. But let me use this as an opportunity to point out what I call my 4 steps in solving problems like this. And this works for all kinds of problems involving Newton's second law. And so step number 1 is this good physical picture, okay? Make sure you really understand what's going on. Otherwise, you don't really know where to proceed on them, and that's the challenge. Then do the free body diagram or diagrams. And so we're getting into some harder problems now. And so diagrams would be appropriate here because we've got 2 objects, okay? Number 3 then is where I say, all right, if you've done these other 2 steps, it makes this next step a little easier to do. And so I like to say, write out the equations. And of course, what I mean by that is basically F equals ma. And so just, write out your equations and then solve them. And so depending on how complicated things are, you might have as simple as 1 equation and 1 unknown to something very complex, like 4 equations and 4 unknowns. I'm not sure this is going to get as complex as 4 equations and 4 unknowns, but I do see here that we have 2 objects. And so when we write out the equations, F equals ma, and there's 1 in the x direction and 1 in the y direction, I'm thinking we're going to have 4 equations here, okay? However, one of them only goes up and down. So I'm kind of thinking 3 equations, 3 unknowns is where this one's going to settle. But you never really know till you kind of follow all these steps. All right, so let's start right here with step number 1. Good physical picture of what's going on here. All right, so I've got this incline. And it says here, if I just kind of read it, it says block number 1 with a mass of 6.72 kilograms. So I'll put that in my diagram here. They label this as capital M. Is then attached to block number 2. Oh, hang on. Let me keep reading. This may not be the 6.72. They just say number 1 and number 2. Let me keep reading. Is attached to number 2 with a spring. Block number 1 is placed on the ramp. Okay, so this is number 1, and this is 6.72 kilograms. So, sorry about that. I kind of freaked out for a moment thinking, okay, wait a minute. The wording here is kind of funny. But block 1, capital M go together with the 6.72. Okay. So this is kind of that first picture, good physical picture of what is trying to be explained here. In fact, the diagram would be helped if we said number 1 here, because again, the diagram is trying to help us get a good physical picture of what's going on. But it's not labeling number 1 here. So we got to get number 1 from the reading. So block number 1, and then this is its mass, is attached to block number 2. So this must be number 2 with a string. Block number 1 is placed on the ramp. So right there is where they make it clear that this is number 1. It's placed on the ramp, which is tilted at an angle of 31.3 degrees and has a static friction of 0.415. All right, so there's some friction involved. The string is run over a pulley, maybe something like that. Yeah. Is run over a massless, frictionless pulley, and block number 2 hangs straight down. The minimum mass that block number 2 can have without the blocks moving is M sub minimum. Now let me pause right there. I hope you're seeing here that if block number 1 is too much, oh sorry, minimum, too little, then this block here ends up pulling it down the hill. So let me just read it again. The minimum mass that block can do without having the blocks move is M minimum. So if this was, say, 0, presumably if this is 0, this would slide down the hill. Now there is some friction, so I guess I need to kind of convince myself that the static friction would be enough to, or not enough to hold it on the hill, and that it would go down the hill. Therefore, something is needed here for a minimum amount. I'm not really sure on that, but again, this is the point of step number 1, trying to get a good physical picture of what's going on. I mean, it's quite possible that the friction would be enough on its own that even with nothing here, it wouldn't go down the hill. And therefore, the minimum would be 0. So that's certainly a possibility. But I'll work on that later on. I'm just trying to get a good physical picture now. Okay. Now, as I read on, it says the maximum mass that block number 2 can have, and so M maximum without the blocks moving is some maximum value. Now, I hope you see the opposite, that if this gets to be so much, it pulls this up the hill. Now, it's got to be quite a bit, because obviously to pull it up the hill, we have to be lifting this one up an incline, and we have to overcome the friction. So it would have to be some value, but there certainly is a maximum value to that. And that's what we're asked to solve. And so basically what we're really saying here is there's some range between the minimum and the maximum that if you put that on here, this would stay. And like I said, if it was the minimum, then this block would be holding it up, but so would the static friction be holding it up. So keep that in mind. And then on the other hand, if this mass is so much and it's trying to, this little number 2 is trying to go down, then it pulls this one up. Of course, resisting it from going up would also be the static friction, because now the static friction would be opposing the direction. And in fact, that's probably one of the most important parts of this step 1 and getting a good physical picture, is realizing why there is a minimum and maximum, why there is this range. And the big thing here is when we're talking about the minimum, then the static friction is up the hill as it tries to slide down. So I'm going to put an F sub S. But when we're talking about the maximum, then the maximum is trying to pull this down, which makes block number 1 go up the hill, and the static friction is in the other direction. And so that's really the important subtlety and the important difference between minimum and maximum, is the direction of that static friction. Now, it's even possible that they have different amounts, because I know the static friction depends upon not just the coefficient, and that doesn't change, but also on the normal force. Now, I don't think the normal force is going to change, but again, I will find that out as I begin to work on my free body diagrams and write out the equation. So I think that the static friction, the magnitude of the static friction, is going to stay the same. Again, difficult to know at this point. And that's not the goal at this point. The goal, again, at this point of step number 1 is just to get a good physical picture of what's going on. Because if you don't get this step right, you're not going to do step 2 right, which leads to step 3 and 4 being wrong also. And so you really got to nail this first one. You really got a good physical picture of what's going on here. Okay, so hopefully in my talking here for 10 minutes, I suppose, that you really kind of nailed this idea of, okay, what is going on? All right, so with that in mind, I can now go ahead. I'm going to get myself a brand new piece of paper here so I can give you a lot of room here. And I'm going to divide it into 4 pieces, really. because I have a free body diagram to deal with for capital M, or block number 1. But I also have a free body diagram for block number 2, or lowercase m. And then, of course, I have 2 scenarios. But why don't we just start with, scenario number 1 here. And that is what would be the minimum, okay? So let's pretend that this block here is going to be sliding down, and so the friction is uphill, okay? So as I draw this free body diagram, I'm going to put block number M kind of at a little angle here. And I am going to draw the forces on it. And my rule of thumb is first draw the force of gravity, so mg, and then everything touching it. Okay, well, the ramp is touching it, so let's call that the normal force. Also, of course, the ramp is touching it with a sideways effort, so that's the static friction. And then also there is a tension from this rope. And really those are just the 2 things touching it, the tension in the rope and the incline, okay? So this right here, a combination of those 2, these are really the components of the forces from the incline, so that's what's touching it. And this is the force from the string, and then this is the force of gravity. So I have gravity and everything touching it. Good. So that's the free body diagram, and that's my step 2. Draw the free body diagrams, plural. Okay. So over here, I would say let's draw the forces on block number 2. Okay, so again, force of gravity, little mg this time, and everything touching it, which the only thing touching it is the tension from the string. Okay, so there it is. All right, so again, that should be fairly easy to draw if you've done a good physical picture. So I'd say, okay, we've done that. We're done with step number 2. So now I can write out the equations. Now, if you followed any of my other videos, you'll know that to write out the equations, what I mean by that is write out all the forces in the x direction and set it equal to ma. Now, that would be a in the x direction. And the reason I split my paper is because then I can say, write out all the forces in the y direction. And that would equal to ma in the y direction. And so that's our 2 sets of forces, but that's for the first block, because I can do the same thing over here. I would have all the forces in the x direction and set that equal to ma. And over here, I would have all the forces in the y directions and set that equal to ma. Now, it's a different A because this is the A in the y direction. Don't confuse it with the x direction. So this is my system of 4 equations. This is why I said earlier that I think I might get 4 equations, although you can see that the left and right of this block, there's nothing of interest. So I really think the left and right, whether we call that x and y, let's decide in a moment, but I don't think is going to become relevant. So I think I'm going to have an x and y for block 1, and then really just the up and down for block 2. Okay, so with that in mind, then let's go ahead and say, all right, let's write out these equations. So again, I'm trying to do step number 3. I'm trying to write out these equations. Now, of course, to do that, I need a grid. I need to say what is the x direction and what is the x direction and what is the y direction. And my hint for you, and continues to be, set up one of your axes in the direction that you actually know, if you know, the acceleration. So now this doesn't have an actual acceleration because we are going to set it up so that it doesn't move, but it's on the cusp of moving. That is, we're trying to find the minimum. That is, if this was any smaller, it would slightly go down the hill. So keeping that in mind, I'm going to do the following. I'm going to say, let's call down the ramp the x direction, which then by default then makes perpendicular the y direction, okay? Now, if I do that, I can apply it to this equation. Now, let me hold off on doing that because let me show you another trick that I like to take advantage of, because this, of course, is a non-conventional coordinate system. We've tilted it. And like I said, you don't have to tilt it, but you really are better off to tilt it. And you're also better off doing this. And this is the first time I've done a problem for you where you have two different objects. I like to keep the pattern throughout the problem the same. And here's what I mean by that. When this one moves down the x-axis, so we'll call that the positive x direction, this one clearly goes up. Now, traditionally, we call up the y direction. But I'm going to go ahead and call up the x direction, which means perpendicular to that is the y direction. Now, again, I know that that means it's an unconventional coordinate system. But what's really nice about this is maybe you can begin to see that this right here is on the cusp of going down in the x direction, and so this x motion corresponds with that x motion. And that's really kind of the beauty of it. Now, this one wouldn't be real hard to just say the x motion here corresponds to the y motion. When this goes down, this goes up. So that wouldn't be too much of a leap. But sometimes these problems can get really hard, and so I like to put x's and have them match. Like I said, this one wouldn't be too bad to say the x here matches with the y here. So I'm not sure there's much of an advantage calling the upward the x direction, but it is the hint I wanted to leave with you. So I'm going to do that and see if that kind of helps as you work on these problems. Okay, so with that in mind, then let's go ahead and now really do step number 3, where we can write out the equations now that we have a grid. All right. Now, on our grid, we need to decide which of these forces are in the x direction. Okay. So, clearly, the force of gravity has a component in the positive x direction. So this would be mg. And if you remember doing this geometry in the last chapter, it's sine of theta, where this right here is theta, which turns out to be the same angle as the slope of the hill. It might be fairly easy to see that if you drop a vertical line here, and knowing that this is theta, then this right here would be 90 minus theta. And so this right here would become a theta. And that's the angle from the vertical that I'm looking at. So this is the theta. And I'm trying to see how much of this force of gravity is opposite of this angle theta. So that's why I'm going to write this as capital mg theta. And it would be down the hill, which I'm calling the positive direction, so there'd be a positive in front. Now, these other two, the tension is pulling it up the hill, so I'm going to put negative magnitude of the tension. I'm going to put negative the force of friction. And then I'm going to put 0 here to indicate that I don't want it to actually move, but I want it on the cusp of moving, okay? So this is a bit tricky here, but watch this. We know it begins to just move when the static friction gets to its maximum. Now, maybe that's worth saying, and I'll come back here to page 1. I didn't put it on here, but one of the lessons you're supposed to be learning here is that static friction is an inequality. It can be a small number up to a big number. So if we are going to mount the minimum amount of mass here, to keep it from going down, the frictional force has to keep getting bigger and bigger and bigger and bigger until it gets to its maximum. Once it reaches its maximum, we take any more off of here and just slides down. So you can maybe kind of imagine we already have some mass on here that is more than the minimum. And that means the upward friction would be less than its maximum, and it would be stationary. And as we take weights off of here, since this is becoming less, the friction's becoming more until some point it gets to its maximum. Once it gets to its maximum, then once we take off another one of this, there's just not enough to hold this up and it slides down. So again, you can see I'm coming back to this first step here, step number 1, which says, got a good physical picture of what's going on. And in this case, the physical picture is what is holding it from going down the hill. And so there's these two that are holding it up the hill. And so as I lower this value, the friction keeps getting bigger and bigger until it gets to that maximum. So it is at this particular value of friction that I would want to know this particular value of the tension that is what's holding it up. And that's probably the key to the step. That's the reading of the math. That's what this math equation means as I go back to the physical picture. So I'm going to put its maximum value for the friction there, which is going to then correspond to the minimum tension that still makes this whole equation come out to be 0. And so the tension up the hill and the friction up the hill equal the component of gravity down the hill, and we still get 0. Okay? That's a big piece of this. And that might be the hardest of all 4 of these. As long as I'm working with the block number 1, let me come down here in the y direction. Here I would have the normal force. That's this force here pushing up. Then I would also have this component of gravity right here, which would be in the negative y direction, and it would be mg cosine theta. And those are the only 2 in the y direction. And that should equal 0 all the time. The way we set up our grid, whether the block moves or not, it only moves in the x direction, does not move into the y direction. And this is why I was saying at the beginning, I think the normal force is going to be a constant and not change. And so sure enough, now I can put in my numbers here. And I will in just a second, but I'm noticing that the sunlight here is going to make a glare. And so let me just, there we go, move my blind a little bit before the glare gets on my piece of paper. Okay, so here I can put in my numbers. So capital M was somewhere back here in this picture, 6.72 times 9.8, and then times cosine of 31.3 degrees. But hang on, I need to check if I'm in degrees mode. Okay, I am. All right, so let me just check if I messed that up. 6.72 times 9.8 times cosine of 31.3 degrees. All right, so this is a normal force of 56.3 newtons. And as long as I'm here, then, that's going to make the static friction, the coefficient of static friction, times the normal. So the coefficient was the 0.415. And so that's 23.4 newtons. Okay. So that's going to be this number right here. That's the most we're ever going to get up the hill. Okay. Now, let's do this number also as long as we're here. Let's do the mg sine theta. If I put in that number, the m is 6.72 times 9.8 times the sine of 31.3 degrees. And so this number is 34.2 minus the tension minus the friction, which we say here is 56.3 equals 0. Now, this is where we come back to a question I said earlier. I'm sorry, I didn't write the friction right. That's the normal force. The friction is 23.4. Okay. And so this is the most you can have up the hill, and we already have this much component down the hill. So that tells me that we have to have some tension. Remember earlier on I asked and said, well, maybe we don't need any weight. Maybe the friction is enough to hold it up on its own, and it doesn't even need any extra weight to hold it. Well, kind of answered that. We do. The frictional force is only 23.4. The force down the hill is 34.2. So, sadly, we know that there is some minimum value. All right. Now, the good thing in this, as I was working out the equations, and I probably went too far. I'm sorry about that. I said write out the equations and then solve them. I haven't wrote out the equation for the second block, and I'm already starting to solve them for the first block. I probably shouldn't have done that. I don't know. I just got excited that this one I could actually solve for. I could solve for n, and then I can get the friction, and then I could come back up to here. And I really haven't even done this other one, wrote it out yet. But as long as I kind of just went to step 4 for the first block already, even though I haven't done step 3 for the second block, let me continue that, because you can see this answers the question of what the tension has to be. This says here then that the tension would have to be this 34.2 minus the 23.4. And that gives me 10.8 newtons. So I guess the good news here for this problem is it wasn't a system of unknowns. I didn't have 3 equations and 3 unknowns, and I had to solve this simultaneously. I certainly going to have 3 sets of equations, but this one I could solve on its own for n. Once I got that, I could solve this on its own for tension. And then once I do that, I can come over here and get the mass. So now let me go back to step 3, but let me explain what I did over here. I actually did step 3 and then to step 4 for block number 1. So now I'm going to come over here for block number 2 and do the same thing. It just turned out that I jumped into 4 for block 1 without writing number 3. So there is no complete order it has to be done, but hopefully that still makes sense to you. All right, so I'm going to come over here and look at the x direction. Now remember, I called upward the x direction, so the tension would be up, so that would be a T pulling it up, and an mg minus down. And again, this would have to be at 0 if we're talking about a scenario where we're not moving. Now, granted, we're on the cusp of not moving. That's why we set the frictional force to its maximum value back here for block number 1. And then, of course, now I can actually then solve this. When I move this over here, I get the tension divided by G is equal to my M. And so I already have the tension as 10.8, so if I divide it by 9.8, it looks like about a 1.1 kilograms comes out to be the answer for the minimum. Now remember, I was doing this all for the minimum. And just for completeness, I'll mention here, there are no forces in the y direction for block number 2. That would be the left and right. And there is no acceleration in the left and right. Yay! So that's true, but useless in solving the problem. And so these are really the three equations that I thought we were going to have. One for the normal force, one for the tension over here, and then one for the friction over here. And fortunately, like I said, it didn't turn out to be a system of equations. I can get N, and then I can get friction, then I get friction, which would lead to tension, and then tension can lead to mass. So it was a kind of an easy set of algebra instead of a hard one. But whether it's easy or hard, solving it is the fourth and big final step in order to get it. All right, now I would say we are halfway done, because we just solved this for the minimum. The other half of this is to say, well, let's solve it for the maximum. What's the difference? Fortunately, not much. So I don't think there's a whole lot I need to repeat. Let's come back here to our good physical picture. And remember, the difference between the minimum and maximum is the following. When we put a maximum, this is going to want to pull it up the hill. And so what's going to happen is the static friction, instead of being up the hill, will be down the hill. So when we go to our free body diagrams, we would be drawing a force of friction down the hill instead of up the hill. So that means when we wrote out this first equations for the sum of the forces in the x direction, down the hill, the positive direction is not only the component of the force of gravity, but also right there would be a plus sign. So that's what would change. There would be a plus sign, and there'd be a plus sign. So that means we would have a different tension. It would look like this instead. We would have the 34.2, instead of subtracting, we would add it together because the force of gravity and the friction are each acting down the hill. So instead of being a tension of 10.8, we would be at 57.6. And as I mentioned earlier, this wouldn't change here. So I could take this over to this side of the equation. And again, nothing would change here in the free body diagrams, so nothing would change in terms of the equation. So if I just take that tension and divide it by 9.8, I would get 5.88 kilograms for what I would call the maximum. And so there's the two answers without having to spend, hopefully, a lot of time in the second time, because there was just a small change in direction. The thinking was still the same. It's just the frictional force was different in direction. And again, that's what I argued back in the good physical picture. Again, that's why really this first step. If you do this first step right, it makes number 2 easy, which makes number 3 easy, which makes number 4 easy. Well, I shouldn't say easy. None of them are easy, especially some of the solving them. That's, sometimes we just, as a physics class, blow it off and forget how hard the math can be. We just say, yeah, whatever. It's just a bunch of math at that point. But it can be hard math. Fortunately, this was not too hard a math. They all kind of fit together real nice. All right, well, I've been talking for a long time, and so maybe I should wrap it up. But there is another way of doing this problem that can be kind of creative. You could have thought of this as one giant object. And so the total mass would be the sum of the two, and the only thing pulling it in kind of a looping direction, whichever way you want to loop it, would be the weight of this one and then the component of that one. I don't know if that's a good way or not. But then the friction only has to do with the weight of that one. And so you got a component of this one and this one, and they're kind of fighting each other. That's the push on the big object. So thinking of it, one big object has some advantages, maybe harder to see it. That's why I decided to go with just two separate ones. I think that's a little easier to see. But of course, when I do two separate ones, I've got to have two free body diagrams, where if I thought of it as one big object, I really only need one free body diagram. But I think it's a little easier to see as two objects. So I'll resist the temptation of trying to solve this as one object, which I think would make easier math, but a little harder to see the physics, and just leave it the way it is and call this good for now. It's been over 35 minutes. All right, take care.